ওকে, সো যদি কখনো শুনতে না পাও আমাকে বলবে, কেমন? এখন শুনতে পাচ্ছ তো?
হ্যাঁ স্যার।
Okay. Now, I talked about this the difference between the statistical mechanics, the way you deal in statistical mechanics with problems that you deal in classical and quantum mechanics, and also I explained how beautifully the largeness of the system is accepted in statistical mechanics, and that is because the quantities that we look for that demands that the system has to be very large, and that is basically thermodynamic limit. And again, I repeat that please do read that paper and get the essence of the four facts where the largeness brings the exact results within the statistical treatment, mechanical treatment. Now, I was trying to give you a concept about the microstates and macrostates. Now, for that, we consider a system with total energy E, and the system consists of আচ্ছা, তোমরা কার্সারটাও দেখতে পাচ্ছ, তাই তো?
হ্যাঁ স্যার।
Okay, so we consider a system with total energy E. The system consists of non-interacting particles. Okay, so actually we will mostly talk about non-interacting particles, and at the end probably we'll talk about interacting particles. Now let us consider a system of a single particle system, and the states for the single particle are like epsilon 1, epsilon 2, and so on. If the system now, so for a particle, given a particle, you have the options to be in any of these states, epsilon 1, epsilon 2, epsilon 3, and it will choose its state depending on its stability. Now, in the system, if you put n number of particles, and of course, as I said in the last class, that till now we have been dealing with the classical statistics, or we are treating the particles classically, and therefore it does not have any objection to occupy any of the states. And therefore, if the system consists of n particles, then let us suppose that n1 particles are occupying the state epsilon 1, n2 particles are occupying the state epsilon 2, and so on, such that the total number of particles is conserved, summation of ni equals to n, and also the total energy is conserved, summation of ni epsilon I equals to E. Okay. So given that, suppose the system, you define the macrostat as NVE. N is the number of particles, V is the volume, and E is the total energy of the system. This is the way you define the macrostat of the system. Okay. So there are, then you see, there are various ways of satisfying this summation n1 ni equals to n, because you have chosen a set of ni, that is n1, n2, n3, etc., etc. You have chosen a set of this ni equals to n, and summation of ni, etc. Now these two relations, total number of particles and total energy, this could be, there could be various sets of ni. One could be, for example, I have written an illustration that you see. Suppose you have a set, n1 particles are occupying epsilon 1, n2 epsilon 2, and so on. Then some of these energies equals to total energy, and some of these particles equals to total number of particles. But it could be that n1 prime particles are occupying epsilon 1. আচ্ছা, কেউ কি ইয়ে করার চেষ্টা করছে, ট্রাইং টু জয়েন? হ্যালো, হ্যালো,
হ্যাঁ স্যার।
কেউ জয়েন করার চেষ্টা করছে?
না তো এরকম কোনো মেসেজ আসেনি, তো বুঝতে পারছি না জয়েন
হ্যাঁ,
করছে কি।
কেউ একজন জয়েন করার চেষ্টা করছে মনে হয়।
টুংটাং করে
আচ্ছা।
আওয়াজ হচ্ছিল, ওই জন্য বলছি আর কি।
কেউ একজন জয়েন করার চেষ্টা করছে হয়তো।
দিয়ে আমাকে আবার সেই প্রেজেন্টেশন মোড থেকে বেরিয়ে গিয়ে আবার জয়েন করাতে হবে, এটাই প্রবলেম।
স্যার রূপক মনে হয়, রূপক।
ও, তাহলে আমি কি করব, প্রেজেন্টেশন মোড থেকে বেরিয়ে গিয়ে আবার জয়েন
আছে
করাতে
মনে
হবে?
হয়,
হ্যাঁ,
কি জানি।
আচ্ছা বাদ দাও, ও তাহলে আমাকে চ্যাট বক্সে বা হোয়াটসঅ্যাপে লিখবে হয়তো। হোয়াটসঅ্যাপটা খুলে রেখে দেখি। না, কেউ কিছু লেখেনি, সুতরাং আই ডোন্ট থিঙ্ক সো। আচ্ছা, so then I can choose another set, say n1 prime, n2 prime, n1 prime number of particles are in epsilon 1, n2 prime number in epsilon 2, and so on, such that this E is satisfied the total energy E and also the total number of particles is there. Now this set n1, n2, n3, this is one set that corresponds to, that satisfies both the total energy and total number conservation. And another set n1 prime, n2 prime, that also
স্যার শুনতে
satisfies,
পেলাম না আগে একটু।
so n1, n2, n3, this set, this set also satisfies the total energy conservation and total number of particle conservation. Similarly, this set n1 prime, n2 prime, this set also satisfies the total energy conservation and total number of particles conservation. And therefore we can say this set n1, n2, n3, this corresponds to a microstate. So I know that so many particles are in this state, so many particles in this state, that those states, individual single particle states, you have the knowledge about the number of particles occupying the single particle states. So this is one set, this is another set, and there could be many other sets like this, and each of these correspond to each of these correspond to the microstates. So for example, this set and this set, these are the microstates. Okay,
হ্যাঁ স্যার, বলছি যে দুজন জয়েন করতে চাইছে বোধহয়।
দুজন জয়েন করতে চাইছে, তাহলে আমি what do I do? I go back. Oh, okay, admit. ঠিক আছে, একজনই তো রয়েছে দেখছি। And where is that? ওকে, ঠিক আছে, দেখতে পাচ্ছ?
হ্যাঁ স্যার।
হ্যাঁ স্যার।
Okay, so these sets, they correspond to a microstate. Okay, and there could be various microstates satisfying these two conservation relations. Now a very important postulate in statistical mechanics is that this is the kind of very fundamental postulate, that all these microstates are equally probable. Any of these states are equally probable. There is no biasness on any of these microstates. Each and every microstate that are states are equally probable. Equal a priori probability is a fundamental postulate and very important postulate in statistical mechanics. Now, so till now, the message I'm giving to you is that if you have a macrostate, if you have a macrostate NVE, then it may correspond to any of these microstates because they are equally probable. Okay, so this is the message that I'm giving till now. Now we can realize that the number of microstates that we denote as this omega, okay, that ohm type omega, we can realize the number of microstates that is denoted by omega as a function of n, v, and e. Okay, simply because this number of microstates will definitely depend on n, v, and e, because if number of particles increases, if total energy increases or varies, and definitely the number of microstates will vary, and if v, the volume, that varies, you understand, if you think of a particle in a box, if v is larger, then the spacing between two energy levels will be smaller, and therefore that way there could be many combinations of n1, n2, n3, and so on, and therefore it will lead to a variation of a number of microstates. That is what I have written here. So omega is a function of the macrostate variables N, V, and E. How do you realize this? That means, how do you realize that this is a function of N, V, E? For that, consider particles in a box or particles in a harmonic trap. Now, if N, V, E, any of these increase, there would be many more sets of N1, N2, and so on, satisfying the summation Ni equals to N and summation Ni epsilon I equals to E, and all the microstates are equally probable. Okay, I think you got the
Hello,
essence.
sir.
Hello, balo.
স্যার ভিটা বুঝতে পারলাম না যে ভি এর সাথে সম্পর্কটা কি।
ভি এর সাথে কে বলছো? নামটা বলবে সব সময়।
অভিষেক।
অভিষেক,
হ্যাঁ।
যদি তোমার ধরো তুমি তোমার একটা এনার্জি আছে, হ্যাঁ, সিস্টেমে একটা পার্টিকেল এনার্জি আছে, একটা পার্টিকেল ধরো, জাস্ট think of a particle. Okay, now you have the states. This is a particle in a box. Now you have the energy states. Okay, now states are separated by some energy. Okay, now if you increase the volume, you increase the length of the box, then your spacing will be very close, right? Very close means the energy levels will be different and they will be very closely spaced energy levels. Then you have more options, to fulfill the total energy by placing the atoms at different combinations of those energy levels. And that's how you can increase the number of microstates. Do you get my point?
হ্যাঁ স্যার।
Okay. Now the connection between statistics and thermodynamics. So basically the essence I'm giving here is that corresponding to a macrostate, there are number of microstates and these microstates are equally probable. And that is a fundamental postulate, that all the microstates are equally probable. Now connection between these two. Now let us see. Now suppose you have the system A1 and A2. Okay, A1 and A2. Now in the right hand side you see the figure, that system A1 and A2, and they are separated by a wall. It's a thin wall. Then let me say that there are number of microstates corresponding to the system A1 is omega 1, which is function of N1, V1, E1, which are the macroscopic variables for the system A. And the system A2 has number of microstates, that is this omega 2, and which is again function of N2, V2, E2, which are the macroscopic parameters of the system A2. Now, let us suppose that A1 and A2 can exchange energy. That means, let's say this wall is kind of conducting wall, separating the two systems. Therefore, E1 and E2 become variable because they exchange energy. Now the composite system is A0 equals to A1 plus A2. That means this is the composite system. You have lifted the boundary. Then this energy will mix, they will exchange energy, and eventually the system that you will compose the system is A1 plus A2, and the total energy would be E1 plus E2 because you had energy E1 in the system A1 and E2 in the system A2, and therefore total energy is conserved because the system is isolated from the surrounding, and therefore this becomes a constant. Now A1 is equally likely to be any one of the microstates omega 1. That is what the fundamental postulate in statistical mechanics I already talked about, and therefore the system A1 is equally likely to be any of the microstates omega 1, and similarly the system A2 is equally likely to be in any of the microstates E2. Therefore, the composite system A0 is likely to be any of the microstates that I denote as omega 0, E1 and E2 equals to omega 1 E1 into omega 2 E2. Because these are the number of microstates, and there is a combination between these. There are many possibilities, and therefore this should be the product. It is like two coins you are tossing. Then what is the probability? Then you multiply both the probabilities, right? Two coins are tossing, you are asking for the probability of appearing this and appearing that. Then you have the product of these probabilities. Similarly, the microstates you have, total microstates of the system would be the product of the microstates of each subsystems, and therefore omega 0 should be omega 1 into omega 2. Now we may write this omega 0 E1 E2 equals to omega 1 E1 and omega 2 E2. If it is E1, if it is E2, then it has to be E0 minus E1 because total energy is conserved. And therefore, omega naught equals to omega naught times omega naught is a function of now, as such, it is function of E naught and E1. One E1 is specified, E2 is automatically specified because E0 is known, that is the total energy, which is constant. Now the question we ask, at what stage of the energy exchange will A1 and A2 be in equilibrium? The answer is the system will reach equilibrium only when omega 0 E1 will attain the maximum value. The philosophy is that the system will assume increasing number of microstates until it reaches a maximum. You know what? That is what I was talking in that day when we are talking about the second law of thermodynamics, that entropy would be maximum. And now probably from this statement you can guess that there could be a connection between the number of microstates and the entropy. But we have to wait for that to get that relation mathematically and physically. Now, if I ask Ovisek, you would respond to my question. Now, I am asking that the system will reach equilibrium only when omega naught E1 will attain maximum number. Now, the philosophy is that the system will assume increasing number of microstates until it reaches maximum. Can you explain that?
হ্যাঁ স্যার,
বলো।
এটার মানে হলো যে সিস্টেমটার ভেতরে যত রকম ভাবে মানে সাজানো সম্ভব। হ্যালো,
বলো।
হ্যাঁ, এটার মানে হলো যে সিস্টেমের কাছে মানে অনেক রকম মাইক্রোস্টেটের চয়েসটা দিয়ে দেওয়া, যে সিস্টেমের কাছে প্রচুর পরিমাণে চয়েস আছে, সেই চয়েসটা যখনই তার কাছে ম্যাক্সিমাম হবে তখনই সে ইকুইলিব্রিয়ামে যাবে। ফর এক্সাম্পল, আমার কাছে তিনটে সংখ্যা আছে, সাপোজ ধরুন 1 2 3, এদের কম্বিনেশন আমার কাছে ধরুন একটাই চয়েস 1 2 3, কিন্তু সিস্টেমের কাছে এই স্টেটটা ইকুইলিব্রিয়াম নয়। সিস্টেমের কাছে যখন 6টা কম্বিনেশন থাকবে, 1 2 3 2 3 1, এই অল পসিবল কম্বিনেশন থাকবে, ম্যাক্সিমাম কম্বিনেশন, সেই স্টেটটা হলো সিস্টেমের পক্ষে সুইটেবল, এবং কম্বিনেশনগুলো বেশি বলে সেখানে সিস্টেমের এন্ট্রপিটাও ম্যাক্সিমাম, তখন সিস্টেমের কাছে চয়েস অনেক। তো এইটুকুই স্যার।
Okay. Samasri, please respond.
Hi, sir.
Respond.
Hi, sir.
Respond. I mean, respond in terms of the question. Answer to the question. Same question.
হ্যাঁ স্যার, চয়েস যত বাড়বে তো মাইক্রোস্টেট গুলো তো ইকুয়ালি প্রবাবিলিটি বাড়বে, মানে তত তো ইকুইলিব্রিয়ামে আসবে। মানে আমার কাছে অভিষেক যে এক্সাম্পলটা দিল আর কি, তো আমার কাছে যদি একটা চয়েস থাকে তাহলে নিশ্চয়ই সেটাকে আমি ইকুইলিব্রিয়াম কন্ডিশন বলবো না। এবার সিস্টেমটা কখন ইকুইলিব্রিয়াম কন্ডিশনে থাকবে, যত আমার নাম্বার অফ চয়েস বাড়াবো, যেটাই আমরা ওই ইকুয়াল প্রায়োরিটি প্রবাবিলিটি দিয়ে আপনি যেটা বললেন যে অ্যাক্সেসেবল মাইক্রোস্টেট করেসপন্ডিং টু আ গিভেন মাইক্রোস্টেট আর ইকুয়ালি প্রবেবল, এটাই তো আমরা জানি। তো সেক্ষেত্রে যত আমরা নাম্বার অফ চয়েস বাড়াবো তো সিস্টেমটা তখন আমরা ইকুইলিব্রিয়ামে থাকবে আর কি।
Can you give an example, in a practical example?
উম, আচ্ছা, আচ্ছা, হ্যালো
Hello?
হ্যালো
হ্যাঁ, শুনতে পাচ্ছ?
হ্যাঁ, হ্যালো
হ্যাঁ, give me a practical example.
হ্যাঁ স্যার, একটা সিম্পল এক্সাম্পল যদি ধরি, দুটো সেল, সাপোজ আই যে দুটো সেল ধরলাম, এবার সেখানে
এত কমপ্লিকেটেড কেন, এত কমপ্লিকেটেড কেন
না
যাচ্ছ?
ওই সেল দুটোতে কটা ডিস্টিংগুইশেবল বলের কথা বলছি, তো এবিসিডি এরকম করে যদি ধরি, তো সেখানে
Okay, just hold on. Okay, I'll give you an
হ্যাঁ,
example, practical example,
হ্যাঁ,
and then you
ঠিক
tell
আছে।
me frankly whether you like the example or not. Okay, you will respond after my explanation is over. Okay, you will respond.
ওকে,
Now, I suppose you are in the class. Okay, you all say 5 or 10 students, they will enter into the class, and then unless someone, suppose the teacher is not there and there is a kind of there is no benches and nothing, you enter into the class, then what will you do? Will you shout? Will you move here and there from this corner to that corner? Now think of a school girls or school boys. Okay, you are quite matured enough, probably you will not be that random, but think of class 5 students. Okay, then and kind of the girls are more oriented, let's say boys, okay, who are kind of naughty. Now let's say some naughty boys are in the classroom and teacher is not there, then you expect that these students, what they will do, they will just run around the class here and then, from one corner to another to another, and so on. Basically it will be a very random and chaotic situation, right? So they will explore every corner of the classroom. But now the teacher comes and he puts a constant on the system. Come on, boys, sit down. I mean, take your seat, be systematic, and so on. I mean, the teacher will speak out, and then they will try to put restraint on the students, and therefore the poor students will come back and they will occupy their own positions. Now see the kind of configurations they had earlier before the teacher entered the class, and the configuration once the teacher entered the class is different, right? Now you have put the constant, and number of configurations have decreased. But now once you put constant on the system cannot go to the equilibrium. They cannot explore the entire world or entire classroom. And in that sense, that if you let the system go on to its own equilibrium, then it will explore each and every corner of the classroom. So that is the what example I wanted to give you, to have a kind of feelings of that reaching the increasing number of microstates until it reaches that the system will assume increasing number of microstates until it reaches maximum. Samasri, respond.
হ্যাঁ স্যার।
So did you understand?
হ্যালো,
Did you understand?
হ্যাঁ স্যার।
Okay, and Abhishek?
হ্যাঁ স্যার।
Okay, all right. And I will also ask Salini. Salini, are you around? Salini, are you around? Shalini should be there. Hello, Shalini. Okay, Nandini. Nandini, are you around? Nandini, can you hear me?
ইয়েস স্যার।
আচ্ছা, তুমি বুঝতে পেরেছো?
হ্যাঁ স্যার।
Okay, all right. আচ্ছা, শালিনী কি হলো? শালিনী কি মানে she is out or Shalini is there? But hello, Shalini, are you around?
স্যার ওর মাইক্রোফোন কাজ করছে না বলছে, ও মেসেজ করছে।
Okay, 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 okay. Oh, I see. Okay, there are chats. My microphone is not working. Okay, okay. All right, okay. Now let's come back to this one. So this is the philosophy behind this. Now, so remember this, that the system will assume increasing number of microstates until it reaches maximum. Now the system with more microstates is more probable, right? And the system with maximum number of microstates is most probable. And therefore, you recall that omega naught equals to omega 1 into omega 2, and therefore you take the derivative with respect to E1. Once you control E1, immediately E2 is controlled because E2 is E0 minus E1 and E0 is constant, and therefore this derivative is omega 2 del omega 1 del E1, omega 1 del omega 2 del E2, del E2 del E1. At equilibrium, say E1 equals to E1 bar and E2 equals to E2 bar, and therefore E1 plus E2 should be equals to E1 bar by E2 bar, and therefore the omega 0 at E1 bar, because this is the energy at equilibrium, and therefore it has to be maximum, because it will try to explore more and more microstates so that the total microstate reaches the maximum value. And therefore del omega del E1, del omega 0 del E1 at E1 bar, E2 bar, that should be equal to 0, and this is the expression for your derivative, and therefore we put the value of E1 equals to E1 bar, E2 equals to E2 bar everywhere, and then eventually we get del omega 1 by del E1, because this should be 0, and therefore I write this del what happened? Yeah, del omega 1 del E1, and then I write omega 2 E2 bar, then this term del omega 2 del E2 and omega 1 E1 bar into del E1 by del E2. You know that E1 plus E2 is constant, and therefore del E1 del E2 by del E1 equals to -1, then you have to put -1 here. Okay, just look at the expression once by yourself. Can I zoom it a little more? Then you can see better through the whole thing. Okay, now you see the expression once. Okay. Okay. Now, so we put this value, and therefore it becomes like this. So -1 is put here, and then we rearrange the terms. Then 1 by omega 1 del omega 1 del E1 at E1 bar, del 1 by omega 2 del omega 2 del E2 E2 bar. Okay, so then you can write it as, in a tricky way, del E1 of ln omega 1 at E1 equals to E1 bar, del E2 ln of omega 2 E2 at E2 equals to E2 bar. It means that this del E of ln omega is a function of E, N, and V. NV is constant. We kept NV constant throughout, and only E varied, and that is equal for the subsystems in equilibrium. In equilibrium, these two values are same, and therefore in general we can write del E ln of omega at constant N and V is constant in equilibrium, and we denote it as beta. Okay, and thus in equilibrium, this beta 1 equals to beta 2. And what kind of equilibrium is this? Abhishek, what kind of equilibrium is this?
Static. No, sorry, dynamic equilibrium.
This is a thermal equilibrium because it is
Oh,
a change
sorry,
in
sorry,
the
sorry,
energy. Okay, it is a thermal equilibrium because you keep N and V constant. Only energy is exchanged, and that is because of the thermal energy is exchanged, right? So this is kind of thermal equilibrium, and this beta actually it is found to be 1 by kBt. Okay, so beta 1 equals to 1 by kBt1, and beta 2 is 1 by kBt2, and therefore T1 equals to T2. Okay, that will come later. So the condition equilibrium is that beta is constant. This is the condition for equilibrium from the statistical approach. Because why statistical approach? Because we started with the microstats, right? We started with the microstats. We did not go through the thermodynamics, right? We went through the we adopted the approach of statistical physics, and therefore by approaching through a statistical approach, we arrived at the condition that beta 1 equals to beta 2, that is del E of ln omega equals to constant when the systems are in equilibrium. Now let us look at it from the entropy point of view, thermodynamic point of view. Okay, now if we look at the same thing from the thermodynamic point of view, by the way, since I'm not doing the board work, I'm going through this. If you feel that you are tired, just let me know. Okay, then in that case I can stop, otherwise I can proceed. Okay, if you feel that it is too much for you, then at that point of view you can tell me. Okay, now the entropy is having entropy, as I said, is an extensive property, right? It is an additive property. Now let us denote the entropy of the subsystem A1 as S1, which is function of N1, V1, E1, and the entropy of the subsystem A2 as S2, which is N2, V2, function of N2, V2, and E2. Okay. Now, during the period of exchange of energy, let's say delta E, which is transformed or transferred, sorry, not transformed, transferred from A1 to A2. The same subsystem I'm thinking of, the same subsystem that I talked about it earlier. This is the system. So A1 and A2, this is the subsystem I'm talking about. Okay. Now, in this subsystem, A1 has this entropy, A2 has this entropy, and delta E amount of energy is transferred from A1 to A2. Then the change in entropy of the composite system should be delta S0 equal to delta S A1, the change of entropy of A1 plus the change of entropy of the system A2. And that is basically delta S1 delta E1 times minus delta E, because energy is transferred from A1 to A2, energy is decreased here, plus del S2 by del E2, N2 V2 of course constant, and delta E because it gains delta E amount of energy. And therefore if you take delta E common, then del S2 del E2 at N1 V1 minus del S1 del E1 N1 V1, that equals to within the closed bracket. Now delta E is a positive and entropy increases. As I said, in the second law of thermodynamics says that entropy increases, and that therefore delta S0 is also greater than 0. Actually it should be greater than equals to 0, and therefore del S2, since this is greater than 0, del S2 del E2 at N2 V2 should be greater than del S1 del E1 at N1 V1. Now what is this? You know from thermodynamics, del S del E at constant N and V is nothing but 1 by T, right? This is the thermodynamic relation. So we are trying to look at it from the thermodynamic point of view, and therefore you see if you write it, it should be 1 by T2 and it should be 1 by T1. So 1 by T2 is greater than 1 by T1, and therefore T1 is greater than T2. Now, if it reaches equilibrium, if the systems are in equilibrium, then this delta S0 should be equals to 0. If A1 and A2 were in equilibrium, then even if you mix them, they will not change the entropy, and therefore delta S will be 0, and therefore T1 should be equals to T2. Therefore, when the systems are equilibrium, so energy exchange will keep on running as long as T1 is greater than T2. However, as it approaches T1 equals to T2, that is, this factor is constant for both this factor is same for both the system subsystems, then the system will reach at equilibrium. And therefore, you see, from statistical approach, we obtain a condition which is beta 1 equals to beta 2, that is beta equals to constant. But in this case, through thermodynamic approach, we obtain that 1 by T is a constant. So this is the condition for equilibrium from the thermodynamic approach. Okay. Now these two approaches we are writing together. Recall the equilibrium conditions obtained from statistical approach as well as thermodynamic approach. So this is the condition obtained from the from the statistical approach, and this is the condition that is obtained from the thermodynamic approach. And therefore, if you take the ratio, beta is a constant, 1 by T is a constant, and therefore if you take the ratio, then that should be, if you take the ratio, then delta E and delta E will go away. It will be delta S by delta of ln omega. That should be 1 by beta T, and that should be constant. Okay, this is constant. Delta S equals by delta ln omega is 1 by beta T. Beta is the quantity which is coming as a condition for equilibrium, that beta should be constant for each system, and T is the temperature. So 1 by beta T is a constant, and since these are constants and this is a constant, this correspondence was first established by Boltzmann, who also believed that since the relationship between two approaches seems to be a fundamental character, the two equilibriums from two approaches, it corresponds to a constant, and therefore, since the relationship between the two approaches seems to be a fundamental character, then the constant must be a universal constant. This constant must be a universal constant. And it was the Planck who first wrote the explicit formula, if you that is the K in terms of this Boltzmann constant, and this constant is identified as the Boltzmann constant Kb. I have written as K, but you can write that K suffix B also, Kb, Boltzmann constant. আমাকে একটু এটা yes, half cup. Now so K is a Boltzmann constant, and if you write it as K, then you can see delta S equals to K delta ln omega. Now if you integrate over on both sides, then S should be K times ln omega. So delta S by delta ln omega equals to constant is a K or Kb, then S should be equals to, so delta of S equals to delta of K ln omega, and therefore you can write S equals to K ln omega. So this is what that I told you, that from second law of thermodynamics you had the statement that the entropy would be maximum at equilibrium, and here you see the number of microstates becomes maximum at equilibrium, and therefore I asked Obisek that there must be a connection between these two, and this connection is this: S, the entropy of a system, is k times ln of the total number of microstates available with that state. So this is a very important relation in statistical mechanics, and this is the connection between the statistics and quantity, microscopic quantity, and the macroscopic quantity. S is the macroscopic quantity, and omega is the microscopic quantity. So these two quantities are connected or are bridged, through this relation. Now, I think did I talk about that? Okay, yeah, I already talked. Now see, so remember, I think you all know about this this relation, but here it is to my satisfaction. I guess I have given you kind of satisfying understanding of the connection between the thermodynamical quantity, that is the entropy of the system, and the microstate of the system. Now think of a situation when, now let us read this one. Thus the formula S equals to K ln omega provides a connection between microscopic and macroscopic macroscopic. Again, note that if the system is frozen to be only in one microstate, that is omega equals to 1, the entropy of the system is 0. As you said in thermodynamics, in the third law of thermodynamics, that when the system, for example, you have the particles in a box, and then you try to reduce the temperature to absolute 0, that means you just freeze the system. That the particles cannot move from its position. Then it is a frozen configuration. You cannot move them from there. That means there is only one configuration. That is only one arrangement. That if there are 3 particles and 3 particles are position 1, 2, 3, and they are frozen. Okay, so therefore you cannot move them from one position to another, and that is the one configuration available to the system at absolute 0, and therefore the omega is 1, only one microstate, and therefore the entropy of the system would be 0. Right? So if a system is in non-equilibrium, then it will always try to explore its microstates. Okay. This provides the theoretical basis of third law of thermodynamics, as I explained. Now you see another way of looking at this relation, S equals to K ln omega. There is a kind of hand waving, you can say, and at the same time it is very physical. Many times I think probably people who deal with this statistical mechanics, probably they try to ask a question like this: that what would be the relation between this entropy? This is the relation we obtain from rigorous argument and calculation. Now without rigorous calculation, just based on some properties of the entropy and the microstates, you can obtain this kind of relation. How? Now look at this. Look at this. Yeah. This is a system A and B. The entropy corresponding to system A is SA. Entropy corresponding to the system B is SB. And therefore, the microstate corresponding to state A is omega SA, and number of microstates corresponding to the B, system B, is omega B. Then if you add these two systems, and then that S is an additive quantity, and therefore it should be SA plus SB. But omega is a multiplicative quantity, as I said, because it's all states are equally probable, and therefore in a combined system it has to be the product of all possible microstates. And therefore now I am asking you, I will not show you. I'll ask you that given the properties that entropy is a additive quantity and omega is a multiplicative quantity, then tell me what relation should prevail between this entropy and the number of microstats. Now I will ask somebody else. Biplav is not there, of course. Now I will ask someone else. Maybe I can ask Sambita Mukherjee. Where is Sambita? Rajesh? Sambita, why don't you speak out? Okay, Rajesh, you were there, right? Rajesh, you were there. Rajesh? Hello, can you hear me? তোমরা শুনতে পাচ্ছ? হ্যালো, কেউ শুনতে পাচ্ছ? হ্যাঁ, so what happened to Rajesh? রাজেশ, আচ্ছা, কে শুনতে পাচ্ছ বলো তো, কে বললে কে শুনতে পাচ্ছ?
ইমতিয়াজ।
স্পিকারটা ঠিক নেই স্যার, সম্বিতা লিখছে। ইমতিয়াজ?
হ্যাঁ স্যার।
ইমতিয়াজ, ওকে। ইমতিয়াজ, ক্যান ইউ টেল মি দ্য রিলেশন?
স্যার ওখানে তো ln এর সাথে রিলেশন আছে, তাই sa plus sb equals to k into ln say omega a plus ln omega b.
Yeah, that's the way you can, you can have the product, because yeah, that is what you are right. That so it should be, you cannot say k ln omega, it should be proportional, right? Sa should be proportional to ln omega a and sb should be proportional to ln b. Then if you say sa, now some constant, you make some proportionality constant which should be same for both the cases because it is a constant for this kind of relation, and therefore you say sa is k ln omega a, sb is k ln omega b, and if you add them, sa plus sb, then it comes as a product. So omega 1 omega b comes as a product. So this is the relation. So based on these two properties, one is the additive one, another is the multiplicative property of microstats. You can easily figure out the relation between s and omega. আচ্ছা, যাদের স্পিকার ঠিক নেই তারা নিশ্চয়ই শুনতে পাচ্ছে, তো শুনতে না পেলে তো মুশকিল, রেসপন্ড না করতে পারছে, বাট they can hear it, right? They can reach me, right?
স্যার সম্মিতা বলছে ও শুনতে পাচ্ছে না, নাকি আওয়াজটা কাটা কাটা আসছে ও বললো।
তাহলে ওর বোধহয় ওখানে নেটের প্রবলেম হতে পারে, বুঝলে তো? ও কোথায় আছে গো? ওর বাড়ি কোথায়?
ওর বাড়ি ঠিক জানি না।
এ বাবা, তোমরা তোমাদের বন্ধুদের বাড়ি যাও না?
কাটোয়া স্যার।
কাটো, ওই জন্যই কেটে গেছে গো, ছাড়ো। যাক, এনিওয়ে, আমার মনে হয় নেট প্রবলেম। Now entropy is a measure of disorder. Okay. Now that is what I think in the last day somebody was talking about it, that entropy that they have learned is entropy is a measure of disorder. I have already explained this. The number of microstates will be more and more if the teacher is not around in a class, in a class of class 5, in a classroom of class 5. When teacher is not around, then as I said, the number of microstates will be more and more because the students will try to explore each and every corner of the classroom, and therefore it's a disorder, right? It's nothing but a disorder. It can be in any of the states possible, right? If the students is allowed to go to each and every position of the classroom, and therefore it's a total chaos, it's a total disorder in that sense. When it explores all macrostates, now it explores only one microstate, then it means that it is just frozen state. Students are not allowed to move from their position. So it is a perfectly one configuration, and therefore that would correspond to omega, the microstate is 1 and entropy is 0. Now you explore a little bit, you allow the students to move little bit, and then it can have some more, it can explore some more microstates because it can change some other positions. And therefore you increase the number of microstates, and therefore you increase the entropy, and therefore you increase the disorder a bit. And this way, if you allow the students, if you relax the constant, if you allow the students to move around the classroom, they will just explore the classroom entirely, and it will be a huge chaos, and therefore total number of microstates will increase, and therefore the total entropy will increase, and the class and the disorder in the class will increase. And that's way, as the microstate is increasing, the entropy is increasing, and hence the disorder of the system is increasing. And in that sense, you say that entropy is a measure of disorder. Okay, Abhishek, respond. Is it clear?
Hello, sir.
হ্যাঁ স্যার,
Is it clear?
হ্যাঁ স্যার।
Hello, sir.
Hello, sir. Hello, madam.
হ্যাঁ, স্যার যেটা বলছিলাম যে একটা
কে বলছো? নাম বলো কে বলছো?
শ্রেয়সী বলছি।
ওকে শ্রেয়সী,
হ্যাঁ, বলছি একটা সিস্টেমের ইকুইলিব্রিয়াম স্টেটে ম্যাক্সিমাম নাম্বার অফ মাইক্রোস্টেট থাকে।
Yes.
আবার ম্যাক্সিমাম নাম্বার অফ মাইক্রোস্টেট থাকলে ইকুইলিব্রিয়ামে তো এন্ট্রপিও বেশি হবে। তাহলে সেটা ইকুইলিব্রিয়াম স্টেট কি করে হচ্ছে?
Non-equilibrium state বলছি না তো, that will correspond to equilibrium state, but the disorder is more.
হ্যাঁ, তাহলে মানে ওটা ইকুইলিব্রিয়াম কি করে হচ্ছে? ডিসঅর্ডার বেশি হলে তো ইকুইলিব্রিয়াম।
No, you are confusing a very very common language you use. You use the language that is not a settling down. The students or the system particles, placed in a systematically is not a equilibrium situation, because once you relax, the system will try to explore. The particles will try to explore all the possibilities in the state, in the box or in the container. In that sense, it is equilibrium. The equilibrium you're talking about, a baby is put under the constant of mother and father to sit or to sleep in a certain bed. That's not a equilibrium, that you are forcing the kid to sleep on that bed for the time. Now if you let the kid free, then kid will move around the room. So that is what is equilibrium. He can go anywhere he likes. It is his equilibrium. It is not your equilibrium. Your burdened equilibrium. It is not your burdened equilibrium or your forceful equilibrium. So in that sense, the way, the language you use in practice in a casual manner is entirely different from what physics talks. Okay, so the equilibrium we're talking about is where the system is free to access all the possible microstates, and when the exploration is exhausted of all the microstates is exhausted, and that state is called the equilibrium state in physics and statistical mechanics. বুঝতে পেরেছো শ্রেয়শ্রী?
হ্যাঁ, ঠিক আছে।
Okay, so till now we stopped till this point, and if you have any questions, anybody, you can raise your question now.
স্যার ইমতিয়াজ বলছি।
Hello.
বলছি স্যার।
Yes, ইমতিয়াজ।
তো এখানে বলেছেন যে enclosed in a container or a spin chain. এই spin chain মানে ঠিক বলছি তো স্যার? এটা মানে কি একটু বুঝলাম না।
তুমি ঠিকই বলছো, তুমি ভুল কেন বলবে? স্পিন চেন ছাড়ো, স্পিন চেন পরে বুঝবে ম্যাগনেটিজম যখন পড়াবো। হ্যাঁ, আমি জাস্ট একটা এক্সাম্পল রেখেছি। হ্যাঁ, ওটা তোমার খুব একটা বুঝে দরকারও নেই। এখানে যেমন পার্টিকেল ইন আ বক্স বলেছি, ওখানে শুধু স্পিন বলেছি। হ্যাঁ, ধরো একটা 1D ল্যাটিস আছে। ওকে, 1D ল্যাটিস। আচ্ছা, আমি এই প্রেজেন্টেশন স্ক্রিনটাকে যদি বন্ধ করতে চাই, এটাকে জাস্ট ক্লোজ করবো, তাই তো? যদি এখানে স্টপ প্রেজেন্টিং করে দিই। হ্যাঁ, now let's come back to the origin. So when I'm talking about the spin chain, that means you think of generally, you know what? If we try to make somebody something understand, then we try to use a very simple system. Let us choose a simple system, 1D chain. You have lattice, or 1D lattice, and in each lattice you have a spin half set, say electrons, let's say. So it can have up state or down state, right? Now,
Huh.
if you allow, now if you increase the if you decrease the temperature forcefully, you know, then what will happen? Or if you don't decrease, if you just forcefully put a magnetic field in certain direction and put all the you force all the spins to point towards the up direction. That is the one configuration, right?
Yes. Huh.
As long as your field is there is no other configuration possible, and therefore in that case the entropy would be 0, because the omega number of microstates is 1, all up,
Yes.
up.
Yes, sir.
But now if you take out the magnetic field slowly, then slowly if you decrease the magnetic field, some of the depending on the temperature, some of the spins will flip.
Yes.
Then you will have, say, n number of, if there are total n number of spins, n1 number of spins in the up direction and n minus n1 number of spins in the downward direction, then you can have many combinations, nc_n1.
Yes, sir.
So those are the combinations. Each combinations are equally likely, and
Yes,
though
sir.
that number corresponds to number of microstates, and therefore
Yes,
the
sir.
microstate will increase. So you don't force, the system will go. This system will travel its own path, and
Yes,
it will try to reach the equilibrium, which is the disorder where half of the spin will be up, half of the spin will be down.
Down.
Okay, that is the most probable situation the system will arrive. And in that sense, I'm talking about the increase of disorder as the system tends to reach the equilibrium. Okay, did you get my point?
Yes, sir.
All right, next, anybody, any question?
স্যার
Yes. What's your name?
স্যার
Please.
স্যার আমি কুন্তল বলছি।
Hello, Kuntal.
হ্যাঁ স্যার, বলছিলাম যে প্রেসার চেঞ্জের সাথে কি কোনোভাবে মাইক্রোস্টেট আমি চেঞ্জ করতে পারি?
কি চেঞ্জের সাথে?
স্যার প্রেসার,
পেপার,
স্যার প্রেসার।
pressure.
হ্যাঁ স্যার, ইয়েস।
Pressure, volume are interrelated actually. They are related. So if you volume changes,
না স্যার আমি হ্যালো,
follow.
হ্যাঁ স্যার বলছি স্যার, ধরুন একটা এক্সাম্পল যেমন দিই, যখন আমি একটা গ্যাসকে লিকুইড করছি বা লিকুইডকে একটা গ্যাস করছি, তো বাই অ্যাপ্লাইং প্রেসার, তো স্যার তখন মাইক্রোস্টেট গুলো কিভাবে চেঞ্জ হচ্ছে?
See, microstate কিভাবে change হচ্ছে, that is a very difficult issue. If all the parameters change, I can give you a flavor how it can change. Now you can just, if you want to understand whether it has an effect on the change of microstates, V and P are interrelated. If volume changing creates a change in microstate, then pressure changing pressure will change the volume, and therefore you can you can understand that they are interrelated, and therefore of course all all parameters, if you change, there should be change in the number of microstates, but how exactly will change, that depends on the problem, and sometimes it could be very complicated. Kuntal,
ওকে স্যার। হ্যাঁ স্যার।
anybody else? So you just Kuntal, you try to understand the basic essence.
স্যার আরেকটা
Yeah, sure, please.
হ্যাঁ স্যার বলছিলাম, স্যার মানে জানি না কোশ্চেনটা ঠিক কিনা, স্যার বলছিলাম প্রেসার চেঞ্জ করে বলছিলাম যে এনার্জি যেগুলো রয়েছে, তো এনার্জি তাদের মধ্যে স্পেসিং এর যদি কিছু চেঞ্জ হয়, তাহলে তো মাইক্রোস্টেট সেগুলো তো চেঞ্জ হতে পারে, নাম্বার অফ মাইক্রোস্টেট ক্যান বি চেঞ্জ।
অবশ্যই that is what I was asking actually, to relate that one parameter is related to another parameter. Okay, so pressure, volume, that they are inversely proportional in a system, so things will change. If you put pressure, the volume will decrease, right? This is a common phenomena, right? So and yeah, that is what I was trying to tell you, or trying to convey. Try to connectivity is very important. Okay,
Yes.
All right. And anybody else?
হ্যালো স্যার আমি তুই বলছিস
স্নিগ্ধা খুলেছে, আরেকজনকে খুলছে মৌসুমী। আচ্ছা, ওকে, ফার্স্ট মৌসুমী and then স্নিগ্ধা maybe. Or স্নিগ্ধা, yeah, মৌসুমী first, yeah.
স্যার বলছি যে বিটা ইকুয়াল টু যেটা আপনি যে দেখালেন যে ডেল ডেল ই অফ এল এন ওমেগা, তো সেখানে আপনি যেটা এট কনস্ট্যান্ট এন এন্ড ভি ছিল ওটাকে থার্মাল ইকুইলিব্রিয়াম বলেছিলেন না থার্মোডাইনামিক ইকুইলিব্রিয়াম বললেন?
Actually thermodynamic equilibrium মানে অনেক কিছু হয়, it is a thermal equilibrium.
ও আচ্ছা, তো ওইখানে এন এন্ড ভিটা কনস্ট্যান্ট থাকার জন্য এটা কি জন্য থার্মাল ইকুইলিব্রিয়াম হচ্ছে ওটা
Because
আরেকবার বলুন।
temperature is different, and that's why energy exchange is taking place.
হুম,
Because only energy exchange is taking place, not mechanical, not chemical, no particle, no volume. পরে আমি বলবো, দেখবে যে পার্টিকেল এক্সচেঞ্জ হলে সেটাকে কেমিক্যাল ইকুইলিব্রিয়াম বলে, যদি ভলিউম ডিফারেন্স হয়, প্রেসার ডিফারেন্স হয় সেটাকে মেকানিক্যাল ইকুইলিব্রিয়াম বলে। ওকে, স্নিগ্ধা প্লিজ।
স্যার যেটা শ্রেয়সী কোয়েশ্চেন করেছিল তো সেটারই একটু আরেকবার রিপিট করুন, মাঝে কেটে গেছিল।
সেই সময় তো সেটা এক্সপ্লেন করার মুড ছিল গো। হ্যাঁ, বলে দিয়েছে। হ্যাঁ, মানে একটা জিনিস যখন ইস্যু আসে না তখন একটা মুড আছে আর কি, বলে দিই। বাট এনিওয়ে আই এম ট্রাইং মাই বেস্ট। হ্যাঁ, প্রশ্নটা আরেকবার করো। শ্রেয়সী যে প্রশ্নটা করেছিল সেই প্রশ্নটা ইজ নট এ কোয়েশ্চেন। ইউ টেল মি ইওর কোয়েশ্চেন, স্নিগ্ধা। ইউ ক্যান রিপিট দ্য কোয়েশ্চেন অলসো।
আসলে আমি কোয়েশ্চেনটা শুনতে পেরেছি, এবার অ্যানসারটা শোনার সময় কেটে গেছিল।
বলো কোয়েশ্চেনটা। Unless you know the question, then what answer do you expect? Tell me the question.
হ্যালো,
Tell me the question. Snigdha, ask me the question. The same question you repeat.
যখন হ্যালো
শুনতে পাচ্ছি, বলো।
এনট্রপিটা যখন ওই বেড়ে যাচ্ছে, যখন ইকুইলিব্রিয়াম স্টেটটা হয়ে যাচ্ছে, তখন এনট্রপিটা বেড়ে গেলে কি করে ওই ইকুইলিব্রিয়াম হচ্ছে স্টেটটা? তাহলে তো ইকুইলিব্রিয়াম হওয়া উচিত না।
না, ইকুইলিব্রিয়াম হওয়া মানে তুমি কি বোঝো?
মানে মোটামুটি স্টেবল থাকবে আর কি, এনট্রপিটা বাড়লে তো ওটা কিছু
স্টেবল থাকা মানে কি? হোয়াট ডু ইউ মিন বাই স্টেবল?
মানে এনট্রপি বাড়তে বাড়তে ওটা ম্যাক্সিমাম হয়ে যাচ্ছে, তাই তো? আর বাড়বে না তার উপর।
আমি যেমন স্পিনের যে এক্সাম্পলটা দিলাম, এটা শুনলে তুমি? যখন আমাকে ইমতিয়াজ প্রশ্ন করেছিল, স্যার স্পিন কনফিগারেশন সম্বন্ধে বলেছেন, তো আমি তাকে উত্তরটা দিলাম, তুমি শুনলে?
ঠিক বুঝতে পারিনি।
দেখো, আমি বলছি যে তোমার একটা টেম্পারেচারে, এট সার্টেন টেম্পারেচারে তুমি একটা ল্যাটিস আছে, তোমার ওয়ান ডিমেনশনাল ল্যাটিস, সেটাতে প্রত্যেকটা সাইটে একটা করে স্পিন আছে, স্পিন হাফ পার্টিকেল আছে, ঠিক আছে? স্পিন হাফ পার্টিকেল মানে কি? যে ওই পার্টিকেলটা আপ স্পিনে থাকতে পারে কিংবা ডাউন স্পিনে থাকতে পারে, তাই তো? নাও তুমি যেটা করলে, তুমি একটা ম্যাগনেটিক ফিল্ড দিলে যাতে করে সব কটা স্পিনই উপর দিকে থাকে, তার মানে তুমি কনস্ট্যান্ট করে রাখছো। এটা হচ্ছে এই ছোট্ট বাচ্চাকে ভুলিয়ে ভালিয়ে ঘুম পাড়ানোর মতো। তাকে তুমি যা খুশি বলে, গান বাজিয়ে করে, যেমন খুশি করে তাকে একদম কনস্ট্যান্ট করে, হ্যাঁ, যত রকম মানে বাহানা করে তাকে তুমি ঘুম পাড়িয়ে রাখলে, তাকে নড়তে চড়তে দিলে না, তার মানে সে ওইখান থেকে আর নড়বে না। ইট ইজ কাইন্ড অফ ম্যাগনেটিক ফিল্ড। বাবা মারা ম্যাগনেটিক ফিল্ড দিয়ে রাখে, বাচ্চা যাতে চুপচাপ ওইখানে শুয়ে থাকে। সেরকম স্পিনগুলোকে তুমি ঘুম পাড়িয়ে রাখলে, মানে একটা ওরিয়েন্টেশনে করে রাখলে, তারা আর অন্যদিকে নড়তে চড়তে পারবে না ম্যাগনেটিক ফিল্ড দিলে। ম্যাগনেটিক ফিল্ডটা কি দিলে? এক্সটার্নাল ফোর্স। তুমি তাকে কনস্ট্যান্ট করে, দিস ইজ নট ইকুইলিব্রিয়াম। তোমার সাধারণ চোখে মনে হবে এটা ইকুইলিব্রিয়াম, কারণ এ তো খুব অ্যারেঞ্জড ওয়েতে আছে। দিস ইজ ইকুইলিব্রিয়াম, দ্যাট ইজ হোয়াট ইউ সে। When the kid is sleeping or he is forced to sleep, then you will say this is equilibrium. But I would say no, it is not equilibrium. It is forceful. You have applied an external force on the kid. You have applied an external force to keep all the spins aligned in the upward direction. Now, if you slowly decrease the magnetic field, then some of them will flip. You know, they will flip because that energy will be better for him, for the system. Once the parents move away from the kid, it will just try to scroll around, around the room, because that kid feels that is better, and the kid enjoys that. Similarly, the spins will flip because they enjoyed that configuration, and therefore, if you totally you take out the magnetic field, eventually you will find that half of the spins, because each spin has equal probability to be on up states or down states. So if you have n number of spins, then the probability of half spin will be up and half spin will be down. Now, if half of the spins are up, half of the spins are down, then you have many choices to arrange them, right? If there are a total n number of spins, then n by 2 is the configuration number of configurations, because n by 2 spins are in the up direction, and n by 2 spins downward direction, and therefore altogether you have so many configurations. Now, once you take away the external force, you let the system to behave freely, it will try to arrange them in such a way that half of the spins will be up and half of the spins will be down, and that will correspond to a huge number of configurations, and that will also correspond to, in your normalize, it will be like a disorder, right? It will be like a disorder, but for the system, that is the preferable state, and that is the equilibrium state. Snigdha, did you follow it?
হ্যাঁ স্যার বুঝতে পেরেছি।
So anybody else, any question? I think let me stop because I have another class, okay? Then see you maybe in the next class, and I'll let you know through WhatsApp, okay? All right, Abhishek?
হ্যাঁ স্যার।
Okay, then let me quit. Thank you so much for your patience.